Okay, so today we're going to be talking about exponential functions. This is going to be section one of a couple different sections revolving around exponential functions. But today what we're going to do is we're going to define and identify exponential functions and find equations for exponential functions using the different components as we've kind of seen with other functions that we've already dealt with before. So the first thing that we're going to talk about is what is an exponential and kind of what it does it look like. So first of all, what we have is that we have our general function here. So this is our general function. And if you notice that it's a times, not ab, but it's a times b to the power of x, where you have the exponential part right here is, if you notice, that x is now in an exponent, not necessarily just by itself or anything else like that. And then we have this a here that we've kind of been looking at in the past, but as of right now, what we can look at it as is kind of a multiplier. So it's just kind of creating a larger function, if you will, but the main component that we're going to be dealing with is this kind of bx, or b to the power of x, and that's what makes it a exponential. And a couple of the components that we have, so a we kind of talked about there is a multiplier. And then this value of b, this is going to be the base for the exponent. So anything else that we've been dealing with as far as what our exponents are and things like that, that's like saying 2 to the power of, let's say, 2, where the base is actually 2. So that's kind of what that value of b is. It's going to be the base of the exponent that we're going to be multiplying continuously for x number of times. So a couple other characteristics. One, just like every other function, it's going to have a y-intercept. This just happens to have a y-intercept at 0, 1. Now the idea behind something like that is that anything to the power of 0 is going to be 1, and so we can always think of 1 as being a value that's going to be there. And it's going to have what we remember as doing a few sections ago with our rational functions, is this is going to have a horizontal asymptote of y equals 0. And so the idea is that there's a couple other things that are in play, and we'll talk about those later. But the idea is that our general functions are going to look like this. They'll never get to be 0. You can't have an exponent that is going to give you a negative number, so that's why we have a horizontal asymptote of 0. And then, so the whole idea of an exponential function is that it's going to grow very rapidly. So as we read this from left to right, as we normally would with any of our other functions, is that it's going to start over here and it's going to kind of go up very slowly, and then once it hits a certain point, it'll start to increase very rapidly. And so that's what we talk about as something being exponential. And so other than what we kind of just talked about is how these values increase very rapidly as you start plugging in larger and larger numbers, we're going to look at some individual examples to show you how these actually behave, how these actually work on a graph. So what we're going to do is we're going to first use our basic form of our y equals a times the base b to the power of x. And so we're just going to do a couple identifications here. So first of all, a in this particular case is 1. There's nothing being multiplied in front of our base. Our base is 2. Now the idea behind this is we're going to take the number 2 and we're going to multiply it repeatedly, one time after another, times 2 times 2 times 2 times 2. That's an exponent. So the first thing that we're going to do is we're going to make a xy table. And we're going to use the generic numbers that we used to use when we were doing all of our other functions, -2, -1, 0, 1, and 2. First of all, we're going to be using 0 because that will give us our y-intercept, and then we'll be able to look at how this performs either on a negative side and a positive side. So let's go ahead and start plugging some stuff in. So as you look at the table that I've created here, so I just started plugging in the value of x as an exponent. Now we looked at some rules of exponents in the past, so we have 2 to the -2 power, and so what that does is that does a reciprocal, and so that's going to be 1 over 4 as an answer. And then 2 to the -1 power is actually 1 over 2. 2 to the 0 power, anything to the 0 power is 1. 2 to the first power is 2, and 2 to the second power is 4. So a couple of things that we do have to remember. We have to remember how exponents behave. And so if you notice, even though we plugged in negative values of x, we didn't get any negative values back as an answer. And so that kind of leads us to how we get a horizontal asymptote. That also leads into, if you notice these values, as you were to increase or as you were to decrease. So as we were to get smaller into the negative, we would just assume that these fractions would just get a lot smaller. And as we plug in bigger numbers here, these values are just going to start growing larger and larger and larger. So what we're going to do is we're just going to go ahead and plot these on our graph here real quick, and then we're going to look at how we can connect these to kind of show our graph and show this particular equation of y equals 2 to the power of x. So I'm going to go ahead and graph these. So we have negative 2 comma 1/4, so it's just a little bit right here. And then we have negative 1 and 1/2. We have 0 comma 1, so that's here. We have 1 comma 2. And then we have 2 comma 4. And if you notice, this kind of looks like the line that we drew earlier. Now the impression here is that we have a horizontal asymptote at what we would consider y equals 0, and we have a y-intercept of 0 comma 1. Now that's exactly what I showed you in the last problem, but that's not necessarily always going to be the case, but in this particular situation this is. So we plotted these out to show this, but the idea is that what we have to understand is that we're not going to get negative values out of this, and that's why we have a horizontal asymptote of 0. Because anything to the power of 0 is 1, that's why our y-intercept is going to be 1. And so we can kind of just plot those values. We notice that they're kind of close together in the first set, but then they start to break apart, and we could keep plotting these out if we wanted to. If I added the next value of x equals 3, that would give me 2 to the third, which is 8. And so we can start to see that they're progressing very rapidly after each successive value of x. Okay, so let's look at a different example. So now when we look at this example that we have in front of us, one of the things that we'll notice is that a is still 1. And in this case, b is actually 1/2. We are taking 1/2 and multiplying it by itself repeatedly. And so now we notice that what we were doing before was a whole number. This time we're using a fraction, and so we're going to see how that's going to be different for us. So again, we're going to make our table of values. We're going to use our classic values of -2, -1, 0, 1, and 2. And then we're going to just go ahead and we're going to plug these values in, do a little bit of work in a column, and then have our final ordered pair. So here we're doing 1/2 to the power of -2. Now you can put this in your calculator if you would like to in exactly that same way. For those of you that don't have a calculator with you right now, you'll have to trust me when I say that you're going to take the reciprocal of this and then you're going to raise it to the power of 2, as we looked at in our exponent rules before. And so this actually ends up being positive 4. 1/2 to the power of -1 ends up being 2. Anything to the power of 0 will give us 1. 1/2 to the power of 1 is 1/2, and then 1/2 to the power of 2 actually gives us 1/4. So if you notice, this is almost I don't want to say the exact opposite of what we were just dealing with, but you can imagine that as we keep going into larger and larger negatives, this number is actually going to get larger and larger and larger. And as we get bigger and bigger positive, our fraction becomes smaller and smaller and smaller. Again, notice that we're not dealing with negative numbers. Even though that we had negative values of x getting plugged in, everything stayed positive, so that's kind of important to see. We had our y-intercept. So again, we had our y-intercept here, and so we can write that down, 0 comma 1. Now notice we're getting smaller and smaller fractions, so we can assume again that our horizontal asymptote will approach 0, and so we have an equation y equals 0. So if we plot that on here, this is what this looks like. So here's our horizontal asymptote, so it won't cross over into negative numbers. And then we can go ahead and plot -2, positive 4, sorry, -1, 2, 0, 1, 1, 1/2, and 2, -2, 1/4. And if you notice, this kind of looks exactly what we were dealing with before, but exactly the opposite. So this one is decreasing from left to right, where our other example So this is decreasing from left to right, where our other example was actually increasing for left or right. So what we end up having is we have two different scenarios. Our graph can either go up or our graph can either go down from left to right, and that will create two different categories of our exponential functions. And here are those categories. So we have two different types of exponentials. We have one that is known as exponential growth, because that is a function in which from left to right, it doesn't matter how it's drawn, but it goes up from left to right. And then we have exponential decay, which is a situation where our graph goes down from left to right. So in order to get that to do that, what we need to have is we need to have b, which is going to be referred to as what is known as a growth factor. Now, a growth factor, in order to make something grow, the idea is that you're multiplying it by a number that is bigger than 1. On the other side, we're going to get what we call a decay factor. Now, in order for something to decay, we need to make it smaller, and so that means that b, this value of b, this base of b, is going to be less than 1, but it also needs to be bigger than 0 for that to work out, because if you notice, none of our values, and if you think about exponentials, it's going to alternate positive and negative if it's negative, and we don't want that to do that. So for a growth factor, we need it bigger than 1. For a decay factor, we need it to be less than 1. So the first one here, we have 72 times 1.6x. We just wanted to decide if this is exponential growth or exponential decay. And we're basically going to say that this is exponential growth, because in this particular case, b is equal to 1.6, which is bigger than 1, so it's growth. In this question, the only number that we're focused on is we're focused on this b. b is 0.8, and so that is decay because it's less than 1. So if we want a number to increase, it's got to be bigger than 1. If we want it to go down, we're going to multiply it by a number less than 1. Kind of think about is marking something up or marking something down. If you want the value to go down, you need to multiply it by something smaller. Now here, again, we're only focused on this value of b, this base of the exponent. And so in this case, the base is 6 over 5, which actually that is exponential growth. Exponential growth is when the number is bigger than 1. 6 over 5 is a mixed number, or not a mixed number, but an improper fraction that is bigger than 1. And then the last one, b is equal to 2/3, and so that means that this is decay. So really what we want to do is we're identifying bigger than 1, smaller than 1. Growth is a b is bigger than 1, decay is a b that is less than 1, but also bigger than 0. And so what we can do with that information is that we can have, or we're given, rates of increase and decrease. And so given the fact that that b is equal to 1 plus the r for our growth, or b is equal to 1 minus the r for a decay, we can use what we call rates of change, not necessarily similar to slope, but we can use values that we're trying to change. So an example of that is I want to change something by 45%. What that means is that r is equal to 0.45, meaning that that's the rate at which I want something to change. Now, if you notice, I want this to go up. That's why I'm signifying it as being positive. And so I want to increase something by 45%. And so in order for me to do that, I need to decide growth or decay. In this case, I want it to go up, so I'm going to use the growth model, which is b equals 1 plus r. And so when I plug this in, I have what is known as a growth factor, because that's what I'm multiplying by. And so in this particular case, my growth factor is going to be 1 plus 0.45, or my growth factor b is going to be 1.45. And so that's what I would use in order to make my values get a lot larger. And so in a sense, I could start making an equation, doesn't matter what it is, y equals a times 1.45 to the power of x. So I can use all of this information that I've been given previously and start building an equation where this value of a just becomes the kind of initial amount, if you will, of what it is that I'm trying to get to be larger or get to be smaller. And so that's kind of how we can change a rate into a what we call a growth factor, or what's going to be also known as a decay factor. So this 1 plus r, this is going to give us a growth factor, and this 1 minus r is going to give us a decay factor. So those are going to be two key terms that we're going to need moving forward. And so here's our examples. So what we're going to do is we're going to make equations in the form y equals b to the power of x. We're going to kind of skip out on a for the time being. And so all we need to do is we need to just decide growth or decay and then figure out our value of b. Remember, we're using b equals 1 plus r, or we're going to be using b equals 1 minus r, depending on the situation. Now, if we look at negative 10%, that means I want it to go down, so that means I need to use decay. And so I'm going to use b equals 1 minus r. Convert this to a decimal, so b equals 1 minus 0.10. Notice that I didn't use the negative, I just used the percentage as it was. And so my decay factor is 0.90, and I can use that now as my equation. Y equals 0.90 to the power of x. So basically we just decide growth, decay, plug it in, and get our equation. And so over here, again, this is negative, so we're going to use our decay method, or our decay equation. So b equals 1 minus r. Convert that 40% to a decimal, so 1 minus 0.40, and then so that gives us a b value of 0.6 or 0.60, and y equals parentheses 0.60 to the power of x. Our last one can be a little tricky if we're not careful. So here we have a plus 200%, so we want to increase, so basically we're going to use the growth model. And so b equals 1 plus r. This 200% is an r, so we just have to convert that, and the r that would go along with this would be, think about how you convert percentages to decimals, 2.00, or just the value of 2. So b equals 1 plus 2. So my b is actually 3 if I want to increase something by 200%. And so my equation, y equals 3 to the power of x. So that's how we create that's how we create equations from just given the rate at which we want to increase or the rate that we want to decrease. Okay. So we have two different types of exponential functions that we need to worry about. And so we have exponential growth, where b is bigger than 1. We have exponential decay, where b is less than 1 but bigger than 0. And really what we're looking at is we're just looking at b. B is either going to be a growth factor. So in this case, b is a growth factor. And in exponential decay, b is a decay factor. And so we're looking at the idea that this value of b, this base of the exponent, is what really has an indication on what our values are going to become, whether they become bigger over time or smaller over time. And so that's going to do it for this video.